This is CA Physics tutorial on thin film interference. In this tutorial we'll define what thin film interference is, and more than anything look at how to calculate thicknesses of films that correspond to constructive and destructive interference. This will apply to oil slicks, soap bubbles, even pressed glass, or something called Newton's rings. Okay, so what is thin film interference? It's, as the name implies, it's an interference pattern that arises not because of diffraction and interference or overlapping waves, so much as we have interference patterns that arise because of reflection. Okay, so you have a light source, either monochromatic, one color, or multicolored white light. It hits a film, which is transparent, and it reflects off of it. And depending on the thickness of the film and the index refractions of the film and the substrate, you can get various interference patterns. So like we said, think of soap bubbles, oil slicks, even DVDs, insect wings can bring out a lot of shimmering colors as shown in these examples here. The reason you would get multiple colors is due to different angles, different thicknesses, etc. But what it all boils down to is you have a path difference. So if you look at this illustration right here, you got incident light coming in. It hits the film. Some of it reflects off the outer surface of the film. Some of the light passes through the film, hits the inner surface, reflects, and these two waves overlap. Now it doesn't look like they're overlapping here because they're shown as separated and at an angle. But what's really happening is the incident light is almost always going to be directly straight down. We can't show it straight down because the reflected rays would be straight up and they'd be overlapping, and we won't be able to see it for illustrative purposes very easily. The film part indicates the transparent medium. The thin is important because what it's basically saying, the thickness T is roughly the same order of magnitude as the wavelength of light. So this is not going to happen with a centimeter slab of glass placed over a surface. We're talking thicknesses that are in the order of tens or hundreds of nanometers, or a little bit more. So we'll see that borne out with certain problems. Okay, so let's take a look at the general approach, because there's no set equation for this. It's just basically looking at path differences. Okay, so we've talked about path differences in the past. We'll do a quick little review here. Okay, between the two reflected rays. So this ray is, in essence, starts reflecting at the surface. The second ray has to travel a certain distance, which is twice the thickness of the film, and then when it comes back out, it's going to again overlap the initial reflected ray. So if that path difference corresponds to being in phase or out of phase with this initial reflected ray, then we can talk about constructive or destructive interference. So if the rays meet in phase, then of course we're going to have constructive interference, as we've seen before. And if they are out of phase, then we're going to get destructive interference. The hard part about this is just determining whether they're meeting in phase or out of phase. That requires a little bit of a procedure to follow, and we'll set that up in a few seconds. Okay, but the basic idea is that you take the path difference. All right, in this case, the path difference in almost all the problems is going to be nothing more than twice the thickness of the film. All right, the wave has to travel T, bounces back another T before it overlaps the initial reflected wave. We basically set that equal to some fraction or whole number of the number of wavelengths of that particular incident light. If it's monochromatic, then that's pretty straightforward. If it's a polychromatic source, then there's multiple wavelengths. So for certain colors, the path difference will match up with a wavelength or a half wavelength or some other multiple of those. We just got to determine what the relevant integer is for our particular problem. All right, so before we can go any further, we have to determine something that happens at the interfaces themselves, and those are phase changes. So that requires a little bit more discussion. All right, if you recall, if I have a slinky where a wave pulse comes in moving to the right, and it hits a rigid boundary, it's going to reflect and it's going to invert. Right? The same thing happens when light. When light hits a certain transparent boundary, it will sometimes invert or go 180 degrees phase change. And the rule for that is fairly simple. If it is incident upon a medium of higher index refraction, then there will be a 180 degree phase change. A trough will become a crest will become a trough. So in other words, N1 has to be less than N2 for this to occur. So that's the process we have to go through every single time before we can set up an equation to determine if there's an inversion. Alright, so for example, in this particular one, which we're going to develop in more numerically in a few minutes, we have air, which is an index refraction of 1. Let's say our film is something greater than 1. Let's say it's 1.3. And then let's say we have glass, which is 1.5. So we can ask ourselves, are there going to be inversions upon hitting the boundaries? Well, at the first boundary, we're trying to enter a higher index refraction. So when this wave reflects, it's going to go through a 180 degree inversion. In other words, a crest has become a trough, very similar to this idea. The second one, boundary, we're going, again, trying to enter a higher index refraction. So when it reflects, this one is going to invert as well. So both these waves, which are overlapping, have inverted. We'll look at the consequences of that later. There are situations, whereas let's say if this one was air, in other words, we just had a soap bubble, whereas air was surrounding it, there would be an inversion on the outer surface, but there would be no inversion on the inner surface because the index refraction of the film is higher than that of air. That's the key to doing these problems, just identifying if there's an inversion, if there's 1 or 2. And rarely are there going to be 0. Okay, the last little tidbit we got to be careful of is that when we do our path difference equals a fractional whole of the wavelength, it's the wavelength not in the air, but the wavelength in the film, because that's the wavelength that's traveling that path difference. And the wavelength in the film is different than the wavelength in the air, and that's how much change there is dependent on the relative indices of refraction. So that the wavelength in n divided by the wavelength originally is going to equal the inverse ratio of the indices of refraction, where N2 is the film index and N1 is generally going to be air, so we're just going to call that 1.00. We can solve for lambda n, and we can see that it's nothing more than the original wavelength, which we'll call lambda 1, and divided by n. We're not going to give it a subscript here, it's just assumed to be the index refraction of the film. So when we do our analysis, you have to make that adjustment. Okay, so let's put it all together for a problem. Okay, so suppose in the diagram above, which we have a thickness, we want to know the thickness of a non-reflective coating. In other words, we're going to take a lens that has made of glass that has an index refraction 1.45, and we want to coat it with a film such that when light of 500 nanometers wavelength hits it, when it reflects off it, it will interfere with itself and completely cancel out. So we get rid of glare, which is a big issue a lot of times in photography. Okay, so going back to our picture from right here, we have a film of a given index refraction. We want to coat it, and so when incident light of a specific wavelength comes in, when it comes back out, it hits this initial reflected wave, and we get complete destructive interference. In other words, no glare. So the way to approach this problem is essentially 3-step. Okay, it's nice to have a diagram, so let's just kind of do a simple schematic. We have air, we have our film, and then we have glass. Okay, we got light coming in, bouncing off, also going through the film, bouncing off, and meeting. Okay, so first question I want to ask, are there going to be inversions at the boundaries? Air to film. Well, our rule is if we're entering a higher index refraction, there is going to be an inversion, so that's a yes for this one. And then from film to glass, okay, glass is a higher index refraction, 1.5 compared to 1.38, so there is an inversion there. Next question we ask, are we looking for constructive interference or destructive interference here? All right, so this is a non-reflective coating, which implies destructive interference. That's going to help set up our equation. Okay, so let's put it all together. What we want to basically say is that our path difference, delta lambda, is going to equal some value of integer of our wavelength in the new medium, lambda n. So the question is, do we want an integer wavelength? Do we want a half integer wavelength? Okay, so here's where it gets a little bit tricky, so follow along. If there had been no inversions at all at either boundary, then it would be our standard destructive interference as a half a wavelength. If there had been one inversion at either boundary, then these two waves would meet out of phase if this was exactly one wavelength. Since there were two inversions right here, two inversions give us essentially the same effect as no inversions. So long story short, if we want destructive interference, we want this to be exactly 1/2 of a wavelength, like your standard destructive interference. So our path difference is nothing more than twice the thickness of the film, as shown in the diagram before. So we have 2t equals 1/2 the wavelength in the film medium. And so if we solve for t, we see that that is nothing more than 1/4 the wavelength in the film, and the 1/4 of the wavelength in the film is going to be the original wavelength divided by the index refraction of the film. So put this all together, we get 1/2. We can leave the wavelength in nanometers, 550 nanometers, divided by the film is 1.38. Okay, punch out the numbers and we see that t is equal to, let's see, 550 divided by 2 divided by 1.38 is almost exactly 200 nanometers. Okay, so once again, if we coat this glass with 200 nanometer film, when the monochromatic light comes in and hits it and then comes back out, it will have traveled twice the thickness of the film, and since there's been two inversions, we want them to be 1/2 a wavelength out of phase with one another, and we get 200 nanometers. Now, most of the times when we're hitting a thin film, we're going to be hitting it with, our films are usually vary in their thickness, so you're going to have a varying T all along here, so different wavelengths are going to interfere at different spots, and so you'll get bands of interference patterns. And if the light isn't polychromatic, you will see shimmering colors. If it's monochromatic, you'll just get alternating bright, dark, as each varying thickness corresponds to a half wavelength, a full wavelength, 3/2, so on and so forth. Okay, the last application is very similar to the first one. And this applies to something called Newton's rings, which I'll show you in class. Essentially what Newton's rings are is you have a curved piece of glass. This is highly exaggerated. Think of a very thin lens touching a flat piece of plate of glass, so that there is an air gap between the curved part of the lens and the glass here. So that air gap is similar to our film from before. So when light strikes the boundary right here, it's going to reflect. Some of the light is going to pass out of the lens through air, hit this, bounce off, and again, if we pretend this is coming in perpendicular, these two rays, ray 1 and ray 2, are going to completely overlap. And since that gap is changing in thickness, there is going to be bands of bright, dark if it's a monochromatic source. So the question we want to ask here is, in this case, what must be the gap distance, or the how much spacing do we have if we want to look at the 5th maximum or the 6th minimum? Like the previous problem, it's basically the same approach. Determine where there are phase changes and then come up with the equation for how path difference relates to an integer or a fraction of the wavelength. Okay, so let's go through this process. Process 1, are there a phase change at R1? So glass is some index refraction, and when our boundaries from glass to air. Now, air is always 1, so glass is going to be higher, so there's going to be no phase change at R1. R2, we're going from air to glass, so glass is a higher index refraction, so there's going to be a phase change at R2. Okay, so this is different than our previous one where we had 2 phase changes. We have 1 phase change. So if this gap was exactly 1 wavelength, somewhere is exactly 1 wavelength of this, we're not going to get constructive interference, we're going to get destructive interference because of this inversion. So our minima are going to occur when our twice the air gap, right, because we got to travel down and back, equals m lambda. Okay, so it's just the opposite of what we talked about when we did diffraction interference or straightforward interference through double slits. Okay, again, because of this, one of the boundaries had an inversion. So it would make sense then the maxima would occur when 2t equals m plus 1/2 lambda, just the opposite. And again, m is going to start off with 0, then 1, so on and so forth. So if we look at right here where there is no gap, that's going to be an area of minimum. Because of the inversion, the path difference is 0, and 0 corresponds to an integer right here, and that corresponds to a minimum. So what we'd expect to see is dark, bright, so on and so forth as the gap gets greater and greater. This will allow us then to work out when the 5th and 6th maximum, 5th max and 6th minimum occur. So I'm going to start with the 6th minimum because that's easier, because we know that when the path difference equals 0 lambda, we have a min. So that's the first one. The 6th minimum would then be when 2t equals 5 lambda. Okay? And we don't have to do the lambda n here because we are traveling in air. That's where that is, and that's going to be the same as the original wavelength. And then for the 5th maximum, that's going to be 2t equals 4.5 wavelengths, because the 5th maximum is going to occur just before the 6th minimum. You can plug in the numbers here. We can see then that the thickness, or the air gap in this case, is going to be 9/4, the original lambda, and here the minimum we're going to have is going to be 5/2 the wavelength. Okay, so 5/2 the wavelength is going to be 1500 nanometers, and 9/4 is going to correspond to 1350 nanometers. Alright, so again, the air gap here is similar to the film that we talked about above. If you do this enough, you can start seeing a pattern emerge. Okay, so if you're talking about if you have either 1 or 2 inversions, we get opposite effects. So when you only have one inversion, either from the initial reflected ray or the second reflected ray, the bright spots are going to occur when 2t, twice the thickness of the air or the film, is equal to m plus 1/2 lambda, and dark will be when 2t equals m lambda, and then reverse here. When you have 2 inversions, that's our normal situation, or similar to normal situation, so we get what we'd expect for bright spots, and then this one is 2t equals m plus 1/2 lambda. And let's not forget the n. It's easy to overlook that, whatever the index refraction is of that film. Okay, so this concludes our introduction to thin film interference.